In this video, we're going to introduce L'Hopital's rule as an extension of the Taylor polynomial work we were seeing earlier. L'Hopital's rule is a tool for evaluating limits. It's important to know how it fits into the general framework of the skills and tools we're using and learning about. In particular, it's not the only tool that we have. We've seen how to handle polynomials over polynomials in a different way, but this is a technique that can be applied when that other technique is not applicable or fails. L'Hopital's rule is perfect for evaluating limits which are in ratio form and have that indeterminate form of 0 over 0, or as we'll see, infinity over infinity. To evaluate a limit like this, when it ends up with a 0 over 0 form, we have to transform the limit somehow. And if this is what we started with, there's a non-obvious relation that says we can replace the original limit with the derivative of the top function over the derivative of the bottom function. Where does that even come from? Well, it comes from our Taylor approximations. If we're evaluating our limit around a, then we can imagine looking at the linearization of our function. It's the value of the function plus the slope times x minus a, and likewise, the bottom function can be approximated by, with g here, the same linearization formula. How does that help us? What we can do is take the limit we're given, x approaches a, of our function f over our other function g, and then replace it with the similar or getting closer and closer to identical linearization. And that doesn't seem initially to help things, but we will be able to tidy this up momentarily. With g prime of a in the bottom. So what we've done here is take a limit of a ratio, which if we try the naive subbing in gives us 0 over 0, and turn it into a new limit. How is that better? Well, if we focus on this f of a and g of a points, if we have x approaching a, then this 0 is what we got from subbing in. So f of a is actually 0 if that's the scenario we're looking at. And likewise, the function value of g, when we plugged in a, gave us 0 as well. Well, in this new form, that means we get zeros and zeros here. Going one step further and tidying that up, we end up with this new ratio, the simplified ratio, with two other terms we can get rid of. And then we see the surprising relationship that when we start with two functions, f and g, and we want to know their limit, when that fails because we end up with an indeterminate form, we can replace that with the limit of the derivatives of the top and the bottom separately. It's important, it's very important at this stage, to separate this from other things that feel a bit similar. L'Hopital's rule is something we do with limits. I want to know what this function is going to head towards as x approaches a. This is not the quotient rule. Yes, it's a quotient, there's a ratio, but it is not the same question. Quotient rule is about computing derivatives. What's the slope of some function? This is, I have a ratio, but I want to know something specific about it. I want to know what value it approaches when I have a limit x approaching a. And this is a way to evaluate that kind of limit. Now that we've seen the background and rationale, let's look at what L'Hopital's rule actually says and how to apply it. If we're evaluating a limit, that's the starting point, that has to be the question we're trying to answer, and we end up with a ratio of the functions that we want to evaluate the limit of, then we of course try the first naive subbing in. If you try that and you get 0 over 0 or infinity over infinity, then you have an indeterminate form. And L'Hopital's rule says, well, that indeterminate form you started with can be traded for the ratio of the derivative of the top and the derivative of the bottom, replacing the original top and bottom. So what this gives us is a very easy way to replace a challenging limit question with something that is hopefully easier to evaluate or that does not lead to an indeterminate form. It's much easier to see in practice, so we're going to look at a few examples. Here we're asked to evaluate a limit. It's already in a ratio form. For this first example, we're going to explicitly label the terms in the same way we did in the last page. So we have a top function f of x which is 1 minus e to the negative 2x. And we have the other function in the denominator, g of x, which is just x. But first, we always try the naive sub-in. Maybe this is not a hard limit to evaluate. We have 1 minus e to the x, and x is approaching 0, so that'll be 1 minus e to the 0, and x approaches 0 in the bottom, that's 0. Is that indeterminate? Yes, it is, because e to the 0 is 1, and so we do get 0 over 0, and that's a problem case. But that makes it a perfect example to try out L'Hopital's rule. So we have our two functions. We can then say, well, if this is indeterminate, maybe using the derivatives will give something not indeterminate. We take the derivative of this function here, and we end up with negative e to the negative 2x times the derivative of the exponent there, the inside, and all over that gives us 2 positive e to the negative 2x when we cancel the negative signs. In a similar way, or simpler way, in fact, g of x is just x, its derivative is just 1. So what can we do with that? We had the limit as x approaches 0 of 1 minus e to the negative 2x all over x. That was indeterminate by itself without manipulation. So what we do is we apply L'Hopital's rule. And L'Hopital's rule says I can swap out, first copy the limit, and then swap out the numerator for its derivative to e to the negative 2x. Then take the denominator, x, swap it out for its derivative, and then we try again. We try the subbing in, and we hope that things got better. It certainly looks like we have good potential, because now when we sub in x approaching 0, we just have 2e to the 0. And 2e to the 0 is just 2. And so we would say the limit here exists and has a very specific value of 2. Again, notice some differences from earlier work. We were not asked for the derivative of this whole function. I didn't care about that. We were just given a function which happened to be a ratio and asked, hey, what value does it go towards? What value does it approach as x gets closer and closer to 0? We couldn't tell from a naive subbing in, so we traded the function that we had originally for a new function through L'Hopital's rule, and that gave us a new ratio that did have a nice limit that we could just evaluate by subbing in. Let's take another example and repeat that process. We're going to use the same function, but this time we're going to have x approaching infinity. So remember, the first step in any limit question is just try to sub in. And in that case here, we're going to end up with 1 minus this term here as x approaches infinity, little side calculation, e to the negative 2x is an exponential decay, so as x approaches infinity, it approaches 0. Oh, so we're going to get a 0 on top, and we're going to approach infinity, so I'm going to take away this equal sign, because this should all be about approaching. And then we realize, oh, this is not indeterminate. This is a perfectly nice limit, and what that nice limit is a scalar value, a finite value up top, and larger numbers, x approaching infinity on the bottom, and so that is heading towards 0. It would be something like the limit as x approaches infinity of 1 over x. What does that approach? Well, I'm dividing by larger and larger numbers, so we get 0. So that's our statement here. Limit as x approaches infinity of 1 minus e to the negative 2x over x is simply 0. And most importantly, no L'Hopital's rule required. Always try the sub in first. L'Hopital's rule only works if you get an indeterminate form. If you get something that has a limit, a well-defined limit, either does not exist or a 0 or a number at the first stage of subbing in, then you're done. Don't overly complicate these. Let's apply this to a new example. This time will involve a trig function cosine. First step, try the naive subbing in. That will give us 1, let's call it approaching. It approaches 1 minus cos of 0. We're approaching 0 for x, and cos of 0 is 1. All right, we have a 0 in the numerator, and we also get a 0 in the denominator. So that's approaching 0 over 0, and that is indeterminate. And if that's the case, then we can start using L'Hopital's rule, and there's nothing else we can really do. We can't use higher powers in the numerator denominator because we have this cosine in there. So what we're going to do is try L'Hopital's rule. For that, we need to label our pieces, or call that f of x. We'll call the bottom g of x. And if we do that, our f prime of x, we'll just do the derivative here, is 1 minus cos as a function, so the derivative is 0 minus derivative of cos is negative sine of 4x. And then we have a 4 inside, so we'll multiply by that. And that'll give us overall positive 4 sine of 4x. Likewise, the g prime, on the denominator we have x squared, its derivative will be just 2x. Perfect. So the limit as x approaches 0 of what we started with, 1 minus cos 4x all over x squared, can now be traded for using L'Hopital's rule. We can trade this indeterminate limit with, or for, x approaching 0 of f prime 4 sine of 4x. And in the denominator, the derivative of that was 2x. If you like, you can do these derivatives in one line. You don't need to break it up into this separate calculation. We do it here more for clarity. All right, so we've traded the limit that was hard for a new limit. And the question is that something we can work with? Let's try subbing in again. That is going to approach, x approaching 0, 4 sine of 0 is approaching 0. Uh-oh. And 0 again in the denominator. This is still indeterminate. Uh-oh. What do we do now? Well, we can ignore where we came from. We can ignore this first step and just say, hey, I'm asked to evaluate this limit. When I do the naive subbing in, I end up with an indeterminate form. What tool would make some sense here? Well, L'Hopital's rule. Let's apply it again. It's still a ratio. Otherwise, we're good to go. So there's no reason we can't apply it again. And this time I will do the calculations a little more shorthand. We'll take the numerator and ask what its derivative is. Actually, let's do the denominator first. The denominator is 2x. Its derivative is just 2. Tidy that x up there. The numerator is a bit more complicated. It has a 4 multiplier. Then the derivative of sine is cosine. 4x stays the same inside. And then the 4x gives us another 4 multiplier. So we started with this indeterminate. We traded it for this using L'Hopital's rule, still indeterminate. We traded it for this form using L'Hopital's rule, and now we'll try to sub in again. And when we do that here, we hit pay dirt. We have 4, cos of 0 is 1, times another 4, all over 2, and all of a sudden we have 16 over 2, which is 8. And that gives us a final value that is finite, so we just work our way back up the chain, and that means our original function, 1 minus cos 4x over x squared, its limit is going to be 8, something that's not at all obvious from the original functions we were working with, but something that we are able to find through, in this case here, 2 applications of L'Hopital's rule. Let's consider one last example. X ln of x, the limit as x approaches 0 from the positive side. Notice we need this positive here because ln of x is only defined for positive x values, x larger than 0. It wouldn't make any sense to do a 2-sided limit around 0 for ln. Let's take a look. Try the naive subbing in. If we do that, we get x approaching 0, that'd be 0, times ln of 0, and a key ingredient here is to remember the graph of ln of x. We've seen this from week 1 onwards. This is ln of x against x, and as we get closer and closer to 0, this graph shoots off towards negative infinity. And this, it's not a ratio, but it's still an indeterminate form. Why? Because I have something that's getting smaller and going to 0, multiply something by something that could be infinitely large, which one of those wins the competition, we can't tell. We have to go back and do more work. All right, so we have the limit as x goes to 0 from the right of x ln of x. This is a bit more problematic than our earlier examples. It's not a ratio of powers. We can't use earlier techniques. It's also not a ratio that L'Hopital's rule works on because it's not a ratio. And L'Hopital's rule requires, going back a few slides here, L'Hopital's rule requires having some function over another function. And then we can talk about the derivatives of each of those. We don't have that here yet. So what we have to do in this case is rewrite it into a ratio so that we can get around this problem. There's pretty much two ways to do this for this example. One is to keep the ln of x on top and then write the other part, the x, as 1 over x. When we tidy all of that up, it's exactly the same as x itself. You could also have done the limit as x goes to 0 from the right of x over 1 over ln of x. That's a totally valid approach. However, that's less appealing because think of what the next step is. L'Hopital's rule says take the derivative of the top and then take the derivative of the bottom. No one wants to take the derivative of this more complicated bottom. It's just a little messier. So we're going to use this form here. But notice how easy it is to create a ratio if there isn't one there already. All right, then we're going to apply L'Hopital's rule and see what it gives us. We have a limit again, but we're allowed to trade this in for the derivative of ln of x on top. Careful, some of these terms are going to look similar. This ln of x, when we differentiate it, gives us 1 over x. And then the 1 over x, you have to be careful with that. The derivative of 1 over x is the same as the derivative of x to the negative 1, which is negative x to the negative 2, or negative 1 over negative exponents means over x squared here. So negative 1 over x squared. Now we're in business. These are all just powers of x. Let's write them in a common single fraction way. We have the 1 over x, and 1 over x squared is just x squared, and there is still a minus sign there. And this we can tidy up a bit before we try to evaluate. We're so close. We end up with simply x negative, and that's it. We have an x squared on top, an x in the bottom. We cancel them, and away we go. Notice by doing the limit as approaching 0, we can do that cancellation because x isn't exactly equal to 0 in this limit. And then we try the naive subbing in. We traded our original limit for a new limit, a new function here, and here there's no problem at all. The limit value is 0. As x approaches 0, this gets smaller and smaller. And so the limit as x approaches 0 from the right of x ln of x, which originally was indeterminate. We had to do more work. That limit exists, and it equals 0. So that's a series of examples of how we can apply L'Hopital's rule to functions that sometimes come already in a ratio format but lead to indeterminate forms, and also functions which are not ratios but indeterminate that we can then manipulate a little bit to make them into something that works with L'Hopital's rule. The best way to improve your skills with this is definitely through applying yourself to the practice problems.